Hi, today we're going to teach you guys how to balance chemical equations. Now, the process with which that I'm going to teach you guys right now may be a little bit different than if your middle school teacher taught you or that you may have found in a book or on a website or in a video. That's because I pretty much came up with this on my own and it seems to work. After teaching for almost 30 years, I've yet to have students that have been unable to balance any of the equations that they've come across. So please follow this system, and I guarantee anything that you're going to find in this class, you'll be able to balance and balance well. All right. So in order to do so, there is a systematic approach that I would like you to please follow. First of all, I want you to write the formulas of the reactants and products to give the unbalanced chemical equation. All right, first thing is if it's given in the names, like if it talks about like methane reacts with oxygen to produce to produce water and carbon dioxide, you would first of all need to make sure that is written down in the chemical formula format. All right. For example, this one, this is ethanol. Burning in oxygen to produce carbon dioxide and water vapor. Now, one thing I would recommend if you're doing this on paper, always do it in pencil, okay? And always write it so that you have enough space in the front of each of the reactants and products for two-digit numbers. Make sure you leave yourself plenty of room. And also, you're going to need some space underneath it as well. All right? So the two-digit numbers that you're going to be writing are the coefficients. Now, coefficient are numbers that are written in front of the chemical formulas in a balanced chemical equation. They indicate the relative numbers of reactants and products in the reaction. And you can apply them and think of coefficients as being individual molecules or formula units of a specific substance, or consequently, you could also think of them as moles, larger representations of each of these, okay? Either way, using the coefficients will help you out. This is what you use in order to balance it, by putting these numbers in front, as I will show you. All right? And remember, it applies to the entire formula. So if I put a number here, all right, in front of the CO2, let's say I put a 2 there. That would apply to just the carbon dioxide. That would mean that I would have, if there's a 2 there, I would have 2 carbons and 4 oxygens. But since it's separated by the plus, any number that I put here in front of the CO2 will not affect the waters. Keep that in mind, all right? So if you have something like this, if you have MgOH2, well, the 2 at the end of the OH and outside the parentheses means that we have 2 of those hydroxide ions, all right? And a 2 in front applies to the entire thing. So the 2 at the end says I have 2 oxygens and 2 hydrogens. But by putting the 2 in the front, that means I multiply all of the subscripts by 2, as it were. And remember, if a subscript is not written, it's considered to have only 1. So by the 2 in the front, the coefficient would distribute all the way across, and I would be ending up with 2 magnesiums, 4 oxygens, and 4 hydrogens. All right? So make sure you got that down. Now, below the equation, basically underneath where the arrow is, the yield arrow, list out each element that is present. All right? Now, don't just list them out in whatever order that they're originally written. This is kind of the key to all this, is that you are to list them out and balance them in order excuse me, of increasing frequency of occurrence. All right? In other words, the elements that are found in the most number of reactants and products should be listed last. So the ones that are listed fewest go first. The ones that are listed most often go last. All right? And then you write down how many of each element is on each side of the equation, reactants and products. So let me show you what I mean by this. So here we have our sample equation again. Now, first of all, carbon. You see how carbon is found in methanol? and it's found in carbon dioxide, and that's it. Bare minimum, a particular element must be found in at least one reactant and one product. All right, one reactant and one product, bare minimum. And if that's the case, you would list it first. Anything that is only found twice can be listed in first. The order of them there does not matter. Just like hydrogen. Hydrogen is found in only two things. It's found in the methanol and it's found in the water. And that's it, only twice. So whether you put carbon then hydrogen or hydrogen then carbon, doesn't matter. What does matter is that you list oxygen last, because if you notice, oxygen is found in 4 separate species. It's found in the methanol. It's all by itself with oxygen here, oxygen molecules. It's found in carbon dioxide, and it's found in water. All right. So I would list them out like this. Okay. I would go carbon first, and I'm sorry, it's supposed to be underneath the arrow. But the carbon comes first, then hydrogen, then oxygen. And then on each side, as you see, I list how many of them there are on that side total. Okay, so like for carbon on the left, this subscript tells me I have 2 carbons, and that's the only carbon that appears on the left side. So that's why I put a 2 here. On the right, there's no subscript, so that means there's only 1 carbon to start off with. Hydrogens, on the left, we have 5 here plus this one over here. It's kind of a weird way of writing, and I know, but it's like an organic compound thing. Since this is a type of alcohol, alcohols always end in an OH, and that tells the chemist, like me, that, hey, look, that's an alcohol, okay? Don't worry about it. You just add them together. 5 and 1 gives you the 6 total on the left. On the right, we have 1, 2 hydrogens, and that's it. Because of that subscript, that means we have 2 hydrogens. And then oxygens, we have on the left 1 oxygen here plus these 2 over here, which means that we have 3. On the right, we have 2 oxygens here plus 1 there. Again, we have a total of 3. And that's why I write a 3 on the right. Now, make sure, again, that you are totaling the number of each element on each side, not just each compound, okay? Now, you're going to then use coefficients, and only coefficients, to make a balanced equation. Now, remember, when it's balanced, that means there are equal numbers of atoms for each element on each side of the equation when an equation is balanced, all right? So when you're looking at it, you want to make sure that, those numbers, let me go back here. When you're looking at it, you want to make sure it's kind of like oxygen here. If you have the same number on both sides, boom, that means that that element is balanced, okay? Now, also keep in mind that whenever a coefficient is added to a reactant or product, you need to be sure to retotal the number of each element in that reactant or product for the entire side, okay? For example, all right, if I were, just as an example, to add a 2 coefficient to the ethanol, since ethanol has carbon, hydrogen, and oxygen, I need to go and then retotal carbon, hydrogen, and oxygen for that side. So like if I put a 2 here, and if you remember, I started off with 2, 6, and 3. Well, when I put a 2 there, that changes carbon, hydrogen, and oxygen, since it's found in the entire thing. So I would go and retotal how many of each one I have. See, for carbon, I would go 2 times 2, and that gives me 4. For hydrogens, since there's 6 here, 2 times 6 gives me 12. And then for oxygens, watch what I do for oxygens. 2 times 2 is 1. 2 times 2, is 2 plus these 2 over here, which gives me 4. All right. And since it's on this side, I didn't change anything on the right-hand side. Okay. So What you do is you basically proceed until you have an equal amount of each element on both sides of the equation. And as you're going down, you need to make sure you balance what's on top first before you move down. And if you do something lower down that throws something higher up, like out of balance, you then go immediately back up to the top and work your way down again. And you just keep doing this. If you go down and it's not balanced, you go back up and you go through again. Go through again. Most of the time, you only have to go through once. Sometimes twice, rarely 3 times or more. Those are the more challenging, harder ones. And you might have a few of those. But for the most part, they're very simple. They just go through once. All right. And as I'll show you a little later on in a sample problem, if you have the same polyatomic ions appearing on both sides of the equation, you can treat them as single units, like monoatomic ions, or you can split them up. So now I'm going to show you guys 3 examples of how to balance chemical equations. The first one is showing methanol burning in oxygen, the one I showed you before, to produce carbon dioxide and water vapor. The second one I'm going to show you is an example of what I was just talking about with the polyatomic ions, and show you both ways of how to do it. And then I'm going to show you an example of a combustion reaction, which sometimes can be a little tricky. All right, so I'm going to have 3 sample problems coming right up. So this video is to show how to balance a chemical equation. We're starting off with unbalanced equation. We have ethanol reacting with oxygen to form carbon dioxide and water. The next step is to list out each element that is present in order of increasing frequency. Now what this means is the fact that carbon appears in only 2 things means we're going to list that first. 2 is the minimum that anything can appear. Next, we can do hydrogen. Hydrogen also appears in only 2 substances. But the fact that oxygen appears in 1, 2, 3, 4 substances is why we have to list and therefore balance oxygen last. Next, we indicate how many of each element there is on each side of the equation, total. On the left, we have 1, 2 carbons. On the right, we only have 1. On the left, we have 5, 6 hydrogens. On the right, we have 2. On the left, we have 1 plus 2 oxygens for 3. And on the right, we have 3 oxygens as well. Now, using only coefficients, we try to balance each element starting at the top and working our way down. So I'm going to start off by putting a 2 next to the carbon dioxide. That way we will have 2 carbons on the right as well as on the left. However, notice how we also, since there's oxygen there, we also must change now the total oxygens on the right. 2 times 2 is 5, plus 1 more is 6. Excuse me. 2 times 2 is 4, plus 1 more is 5. Got ahead of myself. Now we do the same thing for hydrogen. We have 6 and we have 2. So we put a 3 there. 3 times 2 gives us 6 hydrogens, but again, it changes how many oxygens there are on the right. Again, we have to retotal it. 2 times 2 is 4, plus 3 more gives us 7. Now, on the left, we have a choice. We can put a number here to give us more oxygens, or we can put a number here to give us more oxygens. Since the carbon and hydrogen are already balanced, and by putting a coefficient there that would throw the carbon and hydrogen out of balance, we are going to want to avoid that if at all possible. So instead, we're going to try and put a coefficient here. Now the question is, what number times 2 plus 1 will give us the 7 that we need on the left? And of course the answer is 3. By putting a 3 there, 3 times 2 is 6, plus 1 gives us 7. Everything is now balanced, and the equation is balanced. And now I'd like to show you a couple more samples that you're going to be coming across, things that might be a little bit challenging and perhaps give you guys a shortcut or two. So in this example, we have iron sulfate, specifically iron 3 sulfate, reacting with potassium hydroxide to produce potassium sulfate and iron 3 hydroxide. Now, when you're looking at this, your first impulse would be, oh man, I got to separate out the iron, the sulfur, the oxygen, the potassium, and hydrogen. And you can separate them all out by their individual elements. However, when you're dealing with a problem like this that has polyatomic ions, you can also keep the polyatomic ions together if they appear in the same format on both sides. So if you notice, SO4, sulfate, appears both on the reactant side and on the product side as SO4. Same thing with hydroxide. It's both here and over here, which means that if we wanted to, we can keep them together. Now, believe it or not, keeping them together makes this a much easier problem than if you were to separate them. Okay, so let me show you guys this. First of all, I want to show it to you as we keep them separate, all right, just to give you an idea about it. All right, so if we were to separate these, we see that iron is in 2 places, so we can start off with iron. Sulfur is in 2 places, then we can do sulfur. Oxygen's in 4 places, so we want to do that last. We have potassium, and then hydrogen, and then oxygen. So iron, we have 2, and over here, iron is 1. All right. Sulfur on the left, because of this 3, the 3 distributes inside, and that means we have 3 sulfurs. Whereas on the right, we only have 1 sulfur. That 4 only applies to the oxygen. Potassiums, we have 1 potassium on the left. On the right, we have 2 potassiums because of that subscript. Hydrogens on the left, we have only 1. On the right, that 3 distributes in, and we have 3. Oxygens, we have 3 times 4 is 12, plus 1 over here, so we have 13 oxygens on the left. On the right, we have 3 oxygens here plus 4 oxygens here, which means that we have 7. So we just start going through and balancing. Iron is 2 here, but 1 there. So we're going to try and put a 2 in front of the iron 3 hydroxide. That changes the iron to a 2, but now we have to recount both oxygen and hydrogen. So we have for hydrogen, 2 times 3 is 6. So now we have 6 hydrogens. Oxygens, 2 times 3 is 6, plus these 4 there. That brings us to 10. Now sulfur, we have 3. We need to have 3 sulfurs on the right, so 3 there will give us the 3 sulfurs. But that also changes both potassium and oxygen. So the potassium is 3 times 2 is 6 potassiums. And then sulfur is already done. And then oxygen, 3 times 4 is 12, plus 2 times 3. So that gives us a total of 18. Now on this side, we have 6 potassiums on the right. We want to have 6 potassiums on the left. So we go and put a 6 in front of the potassium hydroxide. That makes that a 6. Hydrogen becomes a 6. And oxygen is 6 plus 4 times 3 is 12, gives us the 18. All right, so as you can see, there is a bit of mathematics, especially with the oxygen. Now, if we go and try the same problem again, but this time keeping together the polyatomic ions, all right, so we have iron. Now, sulfate, SO4, all right, SO4 we're going to keep together. Potassium, and then hydroxide, OH. So on the left, we have 2 irons. On the right, 1. Sulfate, we have 3. No multiplication necessary, just whatever the number is on the outside of the parentheses. So we have 3 there. There's no parentheses here, so we only have 1 sulfate on the right. Potassium, we have 1 on the left. On the right, we have 2. Hydroxides, we have 1 on the left since there's no parentheses, but on the right, we have 3. So we just go through like we normally do. We have a 2 and a 1. We put a 2 there, gives us 2 irons. 2 times 3 gives us 6 hydroxides. Sulfates, 3 and 1. We're going to put a 3 in front of the potassium sulfate. That will give us 3 SO4s, but that will also give us 6 potassiums. And then we just finish off by going 6 in front of the potassium hydroxide, make 6 of that, and 6 hydroxides. And now it's balanced. And as you can see, a lot less multiplication, and we end up with exactly the same final answer. Now, when you're doing these, you are allowed to do either way, whichever way makes more sense to you. I just wanted to show you this shortcut way. They go faster and it makes the math a little bit easier, in my opinion. Now, the last one I want to show you is a sample of a combustion reaction. Now, remember, combustion reactions are whenever you have a hydrocarbon, any compound with both carbon and hydrogen. It could also have oxygen or other things. But if it has carbon and hydrogen, and it reacts with oxygen gas, O2, it will always produce carbon dioxide and water vapor. So this is a combustion reaction. And these can be a little bit tricky because of the fact that we may have to scale up, as you will see. So we're just going to list them out in order of frequency. Carbon's found in only 2 things. Hydrogen's found in only 2 things. But oxygen's found in 3 species. So we put that last. On the left, we have 6 carbons, 14 hydrogens, and oxygens, we have 2. On the right, we have 1 carbon, 2 hydrogens, and 3 oxygens. So we start off easily enough. We put a 6 in front of the carbon dioxide, makes that a 6. Oxygen, 6 times 2 plus 1 is 13. Now hydrogens, we have 14 and 2. So by putting a 7 in front of the water, 7 times 2 gives us 14. But oxygens, we have 12 here plus 7 gives us 19. Now this is where you have the difficulty, because if you notice, we only have oxygen here, and because of its O2, oxygens on the left have to be a power of 2, a multiple of 2, as it were. Excuse me. So there's no number that we can put here, no whole number at least that we can put here, that will give us 19 on the left. So this is what you can do. Since there's no oxygen any other way, and there's no way of getting 19 otherwise, temporarily, even though you're not supposed to do this and leave it like that, we're going to put a fraction. So what number times 2 equals 19? Well, 19 divided by 2 is 9.5. So if I put a 9.5, that gives me the 19. Now, it may look balanced down here, but we cannot keep a fraction, a decimal, as a coefficient. So what can we do to get rid of that 0.5 and yet maintain the same ratio of 1 to 9.5 to 6 to 7? What you do is you just basically look at each one and you double each of the coefficients. So this becomes 2. All right. 9.5 becomes 19. 6 we erase to become 12. and 7 we erase to become 14. Now we double check. Since we doubled everything, there's 12, 28, and then that's 38. On the right, we have 12. 14 times 2 is 28. And then 12 times 2 is 24. Plus 14 is 38. And we end up with a balanced chemical equation and whole numbers. And remember, when balancing, you always have to end up with the lowest whole number ratio of coefficients. If I were like, for example, to double it again and have like 4 and 38 and 24 and 28 here, that would technically not be correct because it's not the lowest whole number ratio. All right, so I hope you have found this interesting. Well, at the very least, helpful. And if you have more questions, please come to tutorial.